Electronic structure and electronic configuration for A-level chemistry. This is a comprehensive guide to understand the electronic structure and how to write the electronic configuration of different atoms and ions, including transition methods. So, first thing is the principal quantum number. So, we know that the atom consists of a nucleus, positively charged nucleus, and it has the electrons which orbit the nucleus in different energy level. The energy levels are labeled with an n value, so n1, 2, 3, and so on. And as we go away from the nucleus, or as the number or the n value increases, then that means the energy of that particular energy level increases as well. N refers to as the principal quantum number or the shell number. So this is the principal quantum number. The principal quantum number defines the location of the energy level or the shell. And this is similar as we learned in the Bohr model for the atom. So what is subshells? So shells are divided into what we call subshells, and these subshells have slightly different energies. There are four different types of subshells. These are designated with letters. They are called S, D, P, D, and F. So each energy level has a certain number of subshells. So if we look at this table, we're going to find that the first shell has only one subshell, which is the S subshell, and the second shell has two, which are 2S and 2P. The third one has three, 3S, 3P, and 3D, and the fourth has 4S, 4P, 4D, and 4F. And if we continue with the fifth, sixth, and seventh, we're going to have the same number, maximum number of subshells, which is 4. Each subshell has a certain number of what we call the orbitals, and each orbital can accommodate a maximum of 2 electrons. So what is an atomic orbital? An atomic orbital is a general region in an atom that an electron is most probably going to reside. So it's where you're going to find the electrons in the subshell or in space. An orbital defines the probability of finding an electron in a three-dimensional space around the nucleus. So orbitals, the S subshell has only one orbital, which means it can accommodate a maximum of 2 electrons because each orbital has a maximum of 2 electrons. The P subshell has 3 orbitals, so there is a maximum of 6 electrons in the P subshell. The D subshell has 5 orbitals, so a maximum of 10 electrons. And the F has 7 orbitals, which means there are a maximum of 14 electrons. Going back to the same table, you're going to find that the first subshell, the first shell, because it only has one subshell, so the total number of electrons, the maximum is 2 electrons. The second one, there will be 8. The third one, maximum of 18, because 2 plus 6 plus 10. And the fourth one, it's 2 plus 6 plus 10 plus 14, so a maximum of 32 electrons. The relative energies of the orbitals that belong to different subshells have different energy, but orbitals of the same subshell will have the same energy. So the p orbital, which has 3 subshells, the p subshell, which has 3 orbitals, all these 3 orbitals have the same energy, but the orbital of the s subshell has different energy than the orbitals in the p subshell. Electrons, when we write the configuration, electrons will fill the subshells with the lower energy first. So looking at the different energy of the different subshells, you're going to find that the 1s orbital has the lowest energy, so this is going to be filled first, and then the 2s, and then the 2p, and then the 3s, and then 3p, and then you expect then to have the 3D to have lower energy than the 4S, but actually 4S has lower energy than the 3D. So when we write the electronic configuration, or when the electron starts to fill the orbitals or the subshells, they're going to fill the 4S before they actually going to fill the 3D. And then after the 3D, they're going to fill the 4P and so on. So this is how the different energies of the different subshells of an electrons are. So electronic configuration, to write the electronic configuration of an atom, we are not going to use only the principal quantum number, but we are also going to use the subshells. So electronic configuration is the arrangement of the electrons in the orbitals of an atom. This is called the electronic configuration of an atom. An electronic configuration will consist of a symbol that contains three pieces of information. The first one is the principal quantum number. So here for hydrogen, for example, hydrogen has the only one energy shell or one principal quantum number, which is 1. So this is 1 first, and then the letter that designate the orbital type. So we know that this is S, so 1s, and then a superscript number that designate the number of electron in that particular subshell. So for hydrogen, it's 1s1. The electronic configuration. To determine the electronic configuration of any atom, we add a number of electrons equal to its atomic number. So we know that the number of electrons in any atom equals to its atomic number, beginning with hydrogen and then continuing across the periodic table. Then you add one electron to the subshell of the lowest available energy. So there's something called also the orbital diagram that can help you to understand more about how the electron fill the subshells or how they fill the orbital. So the orbital diagram is a pictogram representation of the electron configuration. It shows the individual orbitals and the pairing arrangement of the electrons. So for example, for hydrogen, hydrogen only contains one electron, so it has only one electron. And we know when we write the electronic configuration of hydrogen, this is going to be 1s1. 1s1 will occupy the orbital of the s. And then what happens next is that the electrons will start to fill the orbitals as we go up with the one with the lowest energy, lowest available energy first, and then it goes up as the energy increases. So helium, for example, there will be two electrons and both of them will be in the 1s. So the electronic configuration of helium is 1s2 with the two electrons as we can see. By the way, the electrons are spinning and the two electrons which fill the same orbital, because each orbital has a maximum of two electrons, will spin in opposite direction. This is why when we write the electrons or represent the electrons in this spectrogram on the or in the orbital diagram, then we will give them different directions, either two arrows in opposite direction like this or just a single headed arrow. Lithium, then when we write the electronic configuration of lithium, there will be two orbitals, two subshells. First one is the 1s2. As you can see, they are filled as paired. And then the 2s1, which going to be unpaired. And then moving on to beryllium, this is 1s2 and 2s2. And then we draw it like this. Moving on then to boron. Boron has now started to fill the p orbital in the 2p. So it's going to be 1s2, 2s2, and then 2p1. So there is a very important rule here that the lowest energy configuration of an atom with electrons within the same set of orbital, that they're going to have the maximum number of unpaired electrons. Meaning, when the electrons starts to fill the p orbital, they are not going to be paired first and then fill another orbital. They're going to fill the orbitals which have the same energy as unpaired first, and then they're going to be paired. So if we look at carbon, for example, there are two electrons in the p orbitals, so these going to fill the two p orbitals as unpaired first. Moving on, nitrogen, 3 unpaired because there are two p3. Oxygen, which has four electrons in the p orbital, so now they are all unpaired. Then the fourth one will start to do pairing to one of the electrons, and then fluorine, which is 2p5, there are two paired, and then the neon, which is going to have six paired electrons. So there is something called the valence electrons and the core electrons. So the valence electrons are important because these are the ones which are in the outer shell energy level, and these are the ones that contribute to the reactivity of the atom. So the electrons occupying the orbitals in the outermost shell, the ones with the highest value of n or the one with the highest energy, these are called the valence electrons. The electrons which occupy the inner shell orbitals are called the core electrons. The core electrons represent a noble gas electron configuration. This is why the electron configuration can be expressed as an abbreviated format by writing the noble gas that matches the core electron configuration along with the valence electron. For example, when we look at sodium, this is the electron configuration of a sodium, which is 1s2, 2s2, 2p2, and then 3s1. These are the valence electrons here, the 3s1, and these core electrons represent the electron configuration of a noble gas, which is neon. So we can write it in abbreviation or abbreviated form where it's neon and then 3s1. Abbreviated electron configuration emphasizes the similarity of the configuration of elements in the same group. For example, group 1, all of them are going to have the electron configuration, abbreviated electron configuration of a noble gas. First one in the group 1 is going to be helium, the second one sodium is neon, the third one potassium is argon, and then all of them will only have one electron in the s subshell of the highest energy level. So 2s1 for lithium, 3s1 for sodium, and then the 4s1 for potassium. Group 2 is the same, but now we're going to have two electrons in the highest subshell, which is the 2s, 3s, or 4s. Now let's have a look at the transition metals. So transition metals, we know that transition metals are these metals which we find them in the center of the periodic table. So what's different about transition metal? Transition metals, they start to add electrons in the d subshell. So they have the highest energy level is the d subshell. So these are called transition metals. The d subshells are filled with a capacity of 10 electrons because they have 5 different orbitals. So they have a maximum capacity of 10 electrons. But after the d, remember that the 4s subshell has lower energy than the 3d. So this is filled first, and then the 3d is filled, and then after that the 4p will be filled. There are some exceptions when we consider the electronic or the electron configuration, which are related to the d orbital filling or which is related to the transition metal. So the exceptions here are the copper and chromium, and you need to know these by heart. So the rule of thumb here is that there is a stability associated with half-filled or fully filled d subshell, which means an electron can shift from the 4s into the 3d subshell to achieve this stability. So we know that the 4s orbital has to be filled first with 2 electrons, then we move to the 3d subshell. So if we are going to achieve a full or a half-filled orbital of the orbital of the 3D, then one electron can move from the 4s into the 3D. So for copper, for example, the expected electronic configuration is the argon and then 4s2 and 3d9. But the actual one is going to be 4s1 and 3d10 because this is the movement of the electron now that has been that happened achieved a full a fully filled subshell of the orbital. Then chromium, so chromium we have argon as well, and then we have 4s2 and then 3d4. So you would expect one electron to move from the 4s2 to the 3d to make it as half filled. So the actual electronic configuration of chromium is argon and then 4s1 and 3d5 because this is more stable. The periodic table arranged the atoms so that the elements with the same chemical and physical properties will be in the same group. We know that the different groups have the same electronic configuration for the valence electrons or have the same number of valence electrons, so they behave similarly in terms of their chemical behavior or their chemical properties. So valence electrons play the most important role in the chemical reaction, and this describes why elements in the same group have similar chemical reactivity because they have similar valence electrons. Main group elements or representative elements are those elements with the valence electrons are found in the s and p orbitals. So these are group 1 to group 7. So these ones, they have their valence electrons are those with the highest n level, meaning they're going to be, for example, if it's group 3, it's going to be the 3s and the 3p. Example of that is gallium. So if you look at gallium here and you look at the electronic configuration of gallium, there is argon and then there is 4s2, 3d10 and 4p1. We know that the 3d has higher energy than the 4s. However, the valence electrons here are the ones in the p and s orbital, not the one in the d orbital. These are not valence electrons for the gallium. Gallium has only three valence electrons. The 10d electrons and the d orbitals, these or on the d subshells, these are counted as core electrons, not as valence electrons. Transition metals or transition elements, they are the metallic elements in which the last electron added enters a d orbital. This is a different story now when we talk about the valence electrons. So the valence electrons for the transition metals will be the electrons in the d orbitals, the last d orbital that has been filled, and also the s orbital that was filled before the d orbitals. So this is which means this is the n minus 1 d orbital and also the n s orbital as well. So for example, if it's in the group 4, it's going the valence electrons are going to be sorry, if we are talking about the period 4, it's going to be the 4s and the 3d electrons. These both are going to be the valence electrons. For example, vanadium. So vanadium has 2 electrons in the 4s orbital and 3 electrons in the 3d orbital. So the valence electrons are 5 electrons, the 4s2 and the 3d3. Now let's think about how to write the electronic configuration of an ion. So we have either a cation or an anion. A cation is the positively charged ion, which is formed by the loss of the electrons from an atom. When an atom loses an electron, normally it loses the valence electrons. It doesn't lose the inner electrons, only the valence electrons. For main group elements, which are the group 1 up to group 7, the electrons that were added last are the first electrons to be removed. So for example, if you have the last electrons in the s and then p, it's going to be the p electrons first and then the s electrons. However, for the transition metals, the highest ns electrons are lost first and then the n minus 1 d electrons. So this is the opposite because we know that the ns electrons are filled first and then the electrons will be filled after that. But when they lose the s electrons first and then the d electrons. So and then we have the anions, which are the negatively charged ions, which are formed when one or more electrons are added to the parent atom. So let's practice and to understand more about how to write the electronic configuration of ions. So these are 4 different ions. First of all, you need to write out the electronic configuration for the parent ion, not the parent atom, not for the ion, and then you start to add or remove the electrons So let's look at sodium. So this is the electronic configuration of sodium. As you can see that this is the valence electron, sodium ion, which is sodium plus. That's going to lose this electron from the 3s1 orbital. So it's going to be 1s2, 2s2, and then 2p6. For phosphorus, this is the electronic configuration of phosphorus. You can see that these two are the valence electrons. The electrons in these two subshells are the valence electron, the ones in the 2s2 and the 3p3. And then when phosphorus gained 3 electrons to give you p3 minus, it will gain 3 electrons and it's going to gain it into the 3p orbital. So this is going to be now the electronic configuration, and we're going to add 3 extra electrons to the p orbital. So we're going to end up with 3p6. Aluminium, so this is the electronic configuration of aluminium. These 3 electrons here in the 3s and the 3p are the valence electrons. Aluminium loses 3 electrons to give you the aluminium 3 plus, and it's going to lose these 3 electrons here, the valence electrons. So when we write the electronic configuration, it's going to be 1s2, 2s2, and 2p6. Now let's have a look at one of the transition metals, which is iron. So this is the electronic configuration of iron. As we can see, the 4s has been written before the 3d because it was filled first and then the 3d was filled next. Iron will lose 2 electrons to give you the iron Fe2 plus. As it does so, it's not going to lose the electrons from the d orbital first, but it's going to lose the electrons from the 4s orbital first. So this is the electronic configuration of Fe2 plus, where it lost 2 electrons from the 4s. There is no 4s here, and it still have all the 6 electrons from the 3d. So what about the iron Fe3 plus? Then it starts to lose 1 electron from the 3d now, so it's going to have the exact same electronic configuration here, and then it's going to be 3d5. So this is for iron 3 plus. So this is the difference between the transition metals and the main group elements.